This video is covering the third part or third day of section 3.2. It's dealing with it's still dealing with linear regression, least squares regression, but it deals with S, which stands for the standard deviation of the residuals, and R squared, which is the coefficient of determination. They're just two more tools that we have to evaluate sort of the appropriateness of using a linear model. How well does the linear model fit the data? Okay, so it's a pretty short video. We're gonna go through these two new tools that we have. All right, so once we create the residual plot, so residual plot, remember that is the plot. It's technically a scatter plot, but it's the explanatory variable or x variable plotted against the residuals. So we don't call this a scatter plot, we call it a residual plot. And so remember that for a residual plot, we're looking for no overall pattern or a random scattering. And if that happens, if we have a random scattering in the residual plot, then that means that a least squares regression line is an appropriate model for our data. So our data is not curved. It falls into a pattern that a line will fit, right? And so now we want to know, like, how well does it fit? And so the S, the standard deviation of the residuals, and the R squared is what we're talking about today. And so these are sort of endeavor to help us decide how well the line fits the data. Okay, so the first thing is the standard deviation of the residuals. So what that means is if I look at all of the residuals, so if I look at, that residual and that residual, that wasn't good, that residual, that residual, that residual, right? I look at all the residual values. The S is the standard deviation of all those residuals. So notice that it doesn't have a subscript on it. S just by itself is going to mean the standard deviation of the residuals. If we meant the standard deviation of, say, the x values, then it would have the S would have a subscript of an x on it. Okay. All right. So we interpret it a lot like we do standard deviations. It's the typical difference from the mean, but here the mean is really this best fit line. Remember that this zero line is, if one of our points was on this residual line, then that means the residual is zero. That means the actual value fell on the best fit line. So it's how far, instead of, standard deviation generally is how far away from the mean the typical data value is. Here, it's basically how off the typical data values will be from the prediction line, okay? This is the formula. We never will ask you to calculate that formula, however, to calculate the standard deviation. It'll be given to you. So in the example of our F-150 pickup trucks, the S was 5,740. All right, so what does that mean, that the S is 5,740? So when we use our least squares regression line to predict the price of the Ford F-150s from the mileage, our prediction will be off, so the difference between the observed and predicted, the prediction will be off by about $5,740. All right, and then the second new tool that we have is called the coefficient of determination. So it's another numerical quantity that will help us decide how well the least squares regression line will be useful for predicting our response variable. So it's R squared. That R is the same R as our correlation coefficient. So if we take R from our correlation coefficient and square it, that gives us the coefficient of determination. So it might just seem like, well, that's weird. It's just the same thing. It's just squared. Well, it sort of is. but the way we interpret it is very different. So first of all, we use percent. We use, it doesn't have any units, but we think of it and we record it as a percent. All right, so the coefficient of determination, or R squared, is the percent of the variation in the values of the y. So think about it's the variation in the y variable that's accounted for by that least squares regression. And again, we have a formula for it here, but again, we're not going to ask you to calculate that. If we know r, we just square it. And if we have r squared, we can square root it to get our coefficient, our correlation coefficient. Okay, but we won't be asking you to use this formula really ever to calculate your r squared. Okay, so let's use some of these ideas. Here we're looking at the example, the SEC football example. So we were using, if you remember, we're using points per game, the average points per game in a season, and using it to predict the number of wins in the season. Okay. So we have a scatter plot of the average points per game for each team, and the number of wins in the season. And so each dot represents one team. And so we know from that, from this data, we can see it's the number of points per game used to predict the number of wins. And then over here we have a residual plot. Again, remember the residual plot is the explanatory variable, which is the average points per game plotted against the residuals. Okay, so A, calculate and interpret the residual for South Carolina, which scored 30.1 points per game and had 11 wins. So let's see if we can figure out which of those points is South Carolina. So I believe it's this point right here, right? So that point looks to be just at 30, a little bit more than 30, 30.1, and it seems to have 11 as the number of wins. Okay, so what we want to do is calculate the residual. So we want to calculate that value, all right? So I'll pause the video, calculate that, and then proceed. Okay, so the residual for the point 30.1 comma 11, that means the observed y value is 11. The y hat, we're going to find that by plugging that into the equation up that they gave us up here. This equation up here is the best fit line, right? So we plug our x of 30.1 in for x, and we calculate it. So you can see here we get the predicted number of wins was 9.4. All right, so the residual is y minus y hat, so 11 minus 9.4, so 1.6. That means, how we interpret that now, that was the residual is positive 1.6, and how we interpret that is that South Carolina scored 1.6 more, right, because it's positive. We don't say we don't interpret it with a plus sign in front of it. We just say South Carolina scored 1.6 more wins in the season than the model predicted. Okay. If it had been negative, we would say South Carolina scored 1.6 less wins or fewer wins in the season than the model predicted. Okay. All right, next one. Is a linear model appropriate for this data? All right, so we can see by looking at the residual plot, there's no overall pattern, or we might say there's a random scattering or no overall pattern in the residual plot, so it means that a line is appropriate. But how well is it appropriate, right? And that's where our S that they gave us up here and our coefficient of determination, R squared, is given up here. Those we're going to use now to help us decide. All right, so interpret the value of S at 1.24. Write it out, pause the video, write it out, and then check how you wrote. Okay, so mine's a little long-winded here. All right, but so when using the linear model to predict the number of wins, we would expect, the number of wins from the points per game, we would expect to be off by about 1.24. Now, my answer is a little longer than that, but we expect the typical difference between the actual number of wins and the predicted number of wins. So in other words, how off is our prediction? We would expect our prediction to be off by this much. So you don't have to write it exactly as this shows. You could shorten it a little bit. So when using our linear model to predict the number of wins from the number of points per game, we would expect our predictions to be off by about 1.24. And remember, S is always positive, unlike residuals, which are positive and negative. Here, S is, standard deviations are always positive. So it's that we would be off by 1.24, but like in either direction, right? Because there's no positive or negative here. Standard deviations are always positive. So we'd either be above it or below it. That's how much we would expect to be off. All right, and then now we want you to interpret the value of r squared. So how would we write that? And so this is a pretty good model here. So we write 0.88, but we write it as a percent. So we'll say 88% of the variation in, and we want to talk about the response, that's the y, is accounted for by the least squares, or the linear model relating, and then those two variables. So pause that and write it, and then compare what I give you. Okay, so about 88% of the variation in the number of wins. So that's the y variable, right? 88% of the variation in the number of wins is accounted for by the least squares regression line of number of wins on points per game. So like relating those two variables. All right, so this is the homework for the third section of the third part of section 3.2. Remember that that's just number 55, 56, 57, and 58 from chapter 3.